Hi, folks. My name is Jamie Kostelnik, and thank you for tuning into the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and co-organized with contributions from Matt Thomas and Stephen Slaughter. For those of you who are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone and video camera. We'll wait until the end of the presentation to take questions. In the meantime, please do your best to make sure your microphone is muted when you aren't intending to speak. It's my pleasure to introduce today's speaker, John Perkins. John received his BS in 2007 from San Francisco State University, where his thesis focused on river incision and sediment transport in Utah. He then spent a few years working at a cosmochemistry lab at UC Berkeley. In 2015, he received his PhD from UC Santa Cruz, where he studied geomorphology and evolution of large caldera systems in the Central Andes. John has been a research geologist at the USGS since he joined as a Mendenhall in 2016. John's work at the USGS focuses on what controls the size and styles of landslides in Northwest Washington State. John, whenever you're ready.
Great. Well, thanks, Jamie, so much for that nice introduction. Hi, everyone. I'm John Perkins, and the work I'm going to talk to you about today is work that was recently published or currently published as a preprint in the EGU journal NHES. And the title of that work, which I've slightly modified here, is Characterizing the Scale of Regional Landsliding in California from Storm Hydrometeorology, which is a bit of a mouthful. But hopefully by the end of the talk, you can see how we've kind of woven these pieces together. And this work really has been a fun sort of collaboration between a group of us here in at the USGS. I'm trying to change my slides here. There we go. And collaborators from the California Geological Survey and the Center for Western Weather and Water Extremes at the Scripps Institute of Oceanography. And so we've been working on various sort of landslide meteorology related problems together. That includes Nina Oakley at CGS and CW3E, Brian Collins here at the survey, Paul Burgess at the California Geological Survey, Sky Corbett, Sam Bartlett at CW3E, and Diane Bryan. And so we've all been kind of motivated with tackling different research threads sort of revolving around this kind of main hypothesis or question, trying to understand whether successful forecasting of rainfall-induced landslide hazards in California requires better understanding of the atmospheric conditions that lead to failure, right? So kind of putting that question more colloquially, can we better understand the conditions of landslide weather? And this is a little bit tricky, especially because in order to successfully do that, we want to understand the sort of landslide hazards across the footprint of an entire storm system, where when you're making landslide inventories, they're typically mapped at a much smaller scale, say 1 to tens of kilometers versus the imprint of a whole storm, which is hundreds of kilometers. And so really what the work I'm going to be discussing today is motivated by that. And the talk is in a few parts. And so part one, we'll be working to sort of calibrate a sort of simple index for mapping landslide hazard potential in space and time, sort of using a very simple soil hydrologic model, looking at local extremes of that as a sort of universal threshold where we can establish distributed shallow landsliding. And so then the second part of the talk is once we sort of have confidence in that index, we can look at the landslide footprint for a series of storms and then start to compare the storm characteristics to the landslide magnitude. So we'll be looking at things like storm frequency and sort of synoptic and mesoscale characteristics of storms. And what that means is sort of the larger sort of storm system scale controls and the sort of finer structural controls within storms. And then part three of this talk, which I've crossed out here because I don't think I have room to talk about it, was going to be focused on sort of circling back to part one and thinking about mechanically in the hill slopes, why is the anomaly, looking at anomalous soil hydrology, important as a sort of universal threshold. So I probably don't have time for that, but if you're interested, you can ask me any questions perhaps. Okay, and so to get us started, so this is a nice photo to give us a sort of context for the system that we're going to be working in. So we're really thinking about shallow landslides occurring kind of within the soil mantle of the landscape. So this is a photo of a shallow landslide taken by Brian Collins in February of 2017 after a pretty strong atmospheric river storm hit the East Bay and triggered thousands of landslides across the East Bay Hills, San Francisco Bay Area. And so you can see here, this is what the headscarp looks like. This is a shallow failure, so it's occurring in the sort of colluvial soil column, and this one sort of ran down and unfortunately destroyed the house below. But so I thought we'd take a little field trip into the headscarp here to kind of better understand the system that we're working in. And so here we're sort of standing now. You can imagine us standing in that headscarp on some sort of bedrock saprolite sort of interface. We'd be staring at a colluvial soil column that's maybe mantled on the top by some plants and a root structure into the soil there. And so when we think about kind of the force balance in this column of soil here, we have the gravitational forces that want to pull that column of soil downslope, and then those forces are resisted by the inherent shear strength of the soil on that lower failure plane at that bedrock sort of saprolite boundary, which sometimes is maybe very discrete and sometimes is more gradational. But in the East Bay Hills where that photo is taken, most of the landslides were occurring in that interface. And so that shear strength that resists failure is often modeled by something called the Coulomb-Terzaghi failure rule, where that shear strength S is a function of a couple different parameters of including the friction angle, which we see on the right, so that tan phi. So that's an inherent granularity property of the soil, right? And then we have on the left, we have that term C, which is a cohesion term. Sometimes it's can be cohesion just due to the soil, say if there's molecular cohesion, if it's a clay soil, for example. And sometimes that C can also be incorporated as a sort of root cohesion terms where the roots coming down into the soil are physically anchoring that material in place. And then, and that term in parentheses is called the effective stress. And this is where groundwater comes in. So normally the shear strength is proportional to the normal stress exerted on that bedrock saprolite interface. But it can be modulated by the water pressure in the soil. So when you rain on the landscape here, let's say you get a water table developing and that water is sort of flowing through the soil column. And if you get positive pore water pressures, that can exert a force on that mineral skeleton, which can lessen the frictional contact on those grains that are supporting the material. And so this is how increasing pore water pressure typically leads to these shallow fails during storms. Right, so if we wanted to do physical modeling of this, we could constrain all these parameters and do that, but it can become problematic doing this over large regions because we have to identify these different variables which can are quite heterogeneous in space. And so typically what people often do, researchers and emergency managers, is rely on more empirically based models, thinking of one of the most common of those being the rainfall intensity duration threshold, right? And so here's an example from Puerto Rico from Simon and Larson. And this is typically where you find some threshold rainfall intensity for a given storm duration that separates rainfall-induced landslide-inducing storms versus those that didn't, right? And so here, what I'm showing, those white boxes here are hurricanes and various tropical storms that did trigger landslides, and those black squares are ones that didn't, right? And so you can typically fit a sort of power law relationship that separates those two populations. And this is usually quite useful, and can be calibrated to specific sites. But thinking about this plot reveals some interesting relationships when we're kind of thinking about the mechanics that we were discussing in the previous slide. For example, when we look at this, we can see, because this is a power law relationship, when we think about the actual amount of water that is the amount of rain that falls that triggers these landslides can be quite different. So if you were just to take this line and integrate it and look at the total amount of rainfall that triggered landslides, we could see that the short duration, high intensity rainfall events require quite a bit less rain than the long duration, short intensity events. And that could mean a couple different things in our system. It could mean that, one, we have wetter soils. So perhaps those landslides on the left here, oh, sorry about that. Let's see if that works again. I was trying to get my laser pointer. There we go. The landslides on the left may have more water already in the soil, and thus are more susceptible to these short duration, high intensity events. But it could also mean, when you have rainfall infiltrating to the soil, it's always draining. So if the infiltration rate of your water is low compared to the drainage rate, it may take a longer time to generate sufficient amount of pore water pressure in order to initiate failure, right? And the last thing is, when we just consider the scale of the length of duration variability in this plot. So we go from events that go from 1 to 2 hours all the way to multiple hundreds or 2 to 300 hours, right? So this actually represents a large range in the scale of atmospheric processes that can trigger landslides, right? And so this example from Puerto Rico is typically dealing with hurricanes and tropical storms. But in California, we have different storm systems that we deal with. So what are the sort of scales of atmospheric processes of different structures that are relevant for thinking about landslides in California? Well, the largest one, as you might have guessed, are thinking about atmospheric rivers. And so this is a nice NASA movie, I think from GO satellite, showing a propagation of an atmospheric river onto the California coast. So these are long filaments of moisture that get swept up from the tropics by these mid-latitude cyclones here and basically get pushed onto the west coast here. And so these are what are called synoptic scale features. So they're hundreds to thousands of kilometers long and kind of on the dynamic scale of days, right? And so these wind up being really important for the water balance of California. And that's visualized in this really nice graphic, if we just focus on the one on the top left here from a paper by Dedinger et al. In 2011, where they show that California is kind of unique among the United States in terms of its precipitation variability. So what this plot is showing here is it's looking at water years. It's the annual water total rainfall from water years for 1951 to 2008, and they're looking at the coefficient of variation across the U.S. So one of the things you see is that California is very unique in terms of its year-to-year rainfall variability compared to the rest of the United States. And even within California itself, from north to south, you see a large gradient where the year-to-year variability is much higher in central and southern California than it is in northern California, and then up to Washington, right, where you have more sort of stratiform precipitation. And one of the reasons that is because California is so dependent on these atmospheric river storms, which are kind of long and thin, and so where they make landfall really matters when considering the overall hydrologic budget of the state. And as you might guess, this can be an important role for triggering landslides if that's where the precipitation is coming from. And there was a very nice study done by Cordera et al. In the in BAMS where they looked at newspaper reports for the San Francisco Bay Area over the past 150 years. And they identified the date of those reports and called them landslide days, and then compared that with atmospheric reanalysis data that looked at this parameter called IVT, which is short for the Integrated Vertical Moisture Transport. Vertical moisture flux. What basically is a measure of moisture in the atmosphere that is kind of used to identify where atmospheric rivers are. And so what they found was that 70 to 80% of the landslide days in the Bay Area over the past 150 years are associated with conditions coincident with atmospheric river type conditions, right? And so, but we also know that not all atmospheric rivers cause storms. So one of the questions that our group has been facing is, what are the sort of processes that govern landslide occurrence during atmospheric river storms and including other storms as well. We have one example from a recent publication a few years ago with that I worked on with colleagues, with Brian Collins, Amy East at the USGS, Nina Oakley, Sky Corbett, and others, where we were sort of able to more precisely identify the sort of structures within an atmospheric river that led to some really intense landsliding near this town of Groveland, which is sort of just west of Yosemite National Park, along the Tuolumne River Canyon. And so this is sort of a map of that IVT parameter showing what an atmospheric river looks like as it makes landfall onto the coast. So you can see this zone of high IVT here, kind of right centered on this town of Groveland. And so this was a storm, and it kept that track basically for the whole storm. And it rained for 2 to 3 days pretty heavily. But the landslides were really localized, and a small section of the Tuolumne River Canyon here, right east of the town of Groveland here. And so this is a Google Earth image showing what those landslides look like. So you can see the hill slopes themselves were extremely, had an extremely strong landslide and sedimentary response to this storm. But you're basically looking at, the 2 to 3 kilometer stretch of river across this whole canyon is the only stretch that had this type of landsliding. And interestingly, this event produced 8 times the annual sediment load along the Tuolumne River just from this one event, right? And so it wasn't until we started looking more closely at the structure of the rainfall that the answer for this became clear. And one of the things we noticed, so we were using radar data here, and what this radar data is showing is the reflectivity values are indicating higher and lower rainfall intensities, red being the highest and sort of green being low intensity rainfall. But we see these really interesting mesoscale structures that are called narrow cold frontal rain bands, or NCFR. And so these are narrow bands of high intensity, very convective precipitation that occur ahead of a cold front. And so these were sort of structures that were interacting with this atmospheric river storm. So they're like 3 to 5 kilometers wide, quite narrow, but really long. And so in this case, this NCFR sort of stalled out over groveland. And it produces sort of intense convective rainfall. And so when we look a little bit more closely, we can look at the rain gauge data. So at this map on the right is showing, there's the polygon sort of extent of those landslides I showed in the previous figure. And here's where the NCFR parked itself. So you get this really nice spatial correlation of where this band of high intensity rainfall sort of acted like a bandsaw in this canyon, which is flowing sort of right to left here in this image. And so, and when you look at the rain gauge data, you get a sense of both the synoptic and mesoscale controls on the rainfall pattern that eventually led to the failure of those slides. So here we can see on March 21st, so this should say 2018, you can see the atmospheric river comes in, rains about 150 millimeters or so. And then sort of at the tail end of the storm, over a period of a few hours, then NCFR comes and basically doubles the rainfall of that event, right? And so, and we did some hydrologic modeling to show that when you look at these independently, neither of them can sort of give you the effect, the similar sort of instability effect than those combined storm elements can. So, right, and so then the question is, you know, we want to build some parameter where we can sort of map these localized changes in space and time. And we know from the research on rainfall intensity duration relationships that these things are usually applied locally, and the thresholds vary from region to region and can depend strongly on what your background climatic conditions are. So people like Ray Wilson and Sue Cannon and others have found that when you normalize the rainfall intensity duration threshold to its mean annual precipitation, you tend to have much better success for that threshold. And so the idea, what we're trying to do here is we want to sort of build a sort of single index that can be sort of continuous in time, that sort of captures the rainfall dynamics involved that yield a relationship, much like a rainfall intensity duration relationship, across the sort of broad climatic regime of California in order to predict landslide prone regions in space and time. And so then with the ultimate goal, once we have a product that we're confident in, we can utilize those maps of landslide areas to learn about which storms kind of cause the biggest impact across the state. So that's sort of the goal of the rest of the talk here, right? And so and our first step to that, we were really motivated by a paper that came out by Odin Mark and others in 2019, where they actually found that looking at the 2-day rainfall anomaly for a given area correlated quite strongly with where you had locations of high density sort of regional landsliding. And so, which suggests that the landscape in some way is sort of geomorphically tuned to its background climate. So for this study, they focused in one area in Japan and on the Kii Peninsula that had a strong landslide response from Typhoon Talis. And what they're showing here, so they mapped a bunch of landslides in high resolution imagery. Those are the red dots. And then, so now they're shown in the middle column as black dots. And so here, Odin's showing the 48-hour rainfall totals here. And so you can see that you can imagine some threshold, that maybe green line, that captures kind of the broad envelope of where the landslides occurred, but there's a lot of gaps in between. But when you normalize that to the background 48-hour rainfall, you have much higher predictive power, where the peaks in this R star parameter correlate more strongly with peaks in landslide spatial density, right? But this was done for one event in Japan. And it was really, really wet. If you look at the middle panel, you can see for the 2-day rainfall totals are in excess of a meter to 1.2 meters. You know, this is not the type of rainfall that we ever see in California. So we weren't sure going into this if we could use a parameter like this that sort of doesn't account for sort of antecedent conditions. And we know in California that soils can be quite dry, and antecedent conditions might matter, right? And that in California, that relationship was shown really nicely from a paper by our Sterling Landslide Hazards Program Seminar Coordinator, Matt Thomas, and others in 2018, where he was working back in the East Bay Hills in California, near where that landslide on the title slide I showed you was. And what he did was use the sort of record of recent landsliding in the area and took a physically based infiltration model, a Richards equation model, and coupled that to a slope stability model and sort of created a deterministic threshold of when you got landslide producing storms and when you didn't, based on two simple parameters. So on the x-axis, you have antecedent soil saturation. And then on the y-axis, you have 72-hour rainfall, so the 3-day rainfall rather than the 2-day. And what he found is when you plot the events in this space, you can get this deterministic sort of nonlinear envelope, this bold black line that separates the landslide producing storms that are in orange, and then the orange sort of section of that plot, to the non-landslide producing storms in the whiter section. So that really strongly suggests that in California, a metric like R-star may not be as applicable because of this antecedent condition exerts such a strong control, right? And so that took us back a couple decades to thinking about utilizing a sort of simple hydrologic index that might capture this, that is of course very simplified compared to using something like a Richards equation model, but might capture the essence of what we're trying to get at in a way that's useful. And so so we looked toward a class of models called hydrologic tank models or leaky barrel models. And this work was sort of pioneered in the landslide world by Ray Wilson and Jerry Wyzurek in the 1990s, where they used a model like this to correlate to pore pressure variations that they had in a landslide early warning site in the Santa Cruz Mountains in California, and then was later utilized by Jonathan Gott and Rex Baum and others as part of a decision tree for a landslide early warning system in Seattle. And so what this model actually is reflected, so we don't pay attention to the equation yet, but we can just look at the barrel here. So it's a really simple model, and all it is you rain into that barrel with an intensity I, and so you start filling that barrel up from the bottom up until you get to a specific height denoted RO, right? And so what that reflects is kind of wetting up of the soil till you get to your like field capacity, right? The amount of water that can be bound in capillarity in the soil. And once you get above that, the more you rain on it, now the water starts to drain out of that pipe at a rate that's proportional to the amount of water you have in the tank above that. So it's actually the same sort of differential equation that's used for radioactive decay, which is kind of funny. But so when you solve that equation, you wind up with an expression like this. And so here on the left, that Z term, that level of water in your system, is represented by this term AWI, or the antecedent water index. And so one of the things that's nice is this is a continuous variable, and it actually as two terms. One that represents a sort of antecedent condition. So here you see a T on the left and then a T-1 in the antecedent rainfall, right? So this is taking the conditions prior to a given time. And then you add in the rainfall intensity in the second term. And this is all modulated by this drainage parameter KD, right? And so this is cool because it's one sort of index that kind of captures rainfall intensity, duration relationships, and has the sort of antecedent effect kind of embedded within it, right? And so from there, we can do something similar to R star and instead make this parameter we call A star, which is just the AWI at time t divided by the 10-year recurrence interval of AWI at that location. The rub with this is that we don't know what the climatology of AWI is across all of California. Excuse me. So we had to build one. And so what I'm going to do now is walk you through that process a little bit. And we're going to start with a really interesting example of a kind of cool enigmatic storm that produced landslides in San Diego in 2020. And so a lot of this work was kind of originally done by Nina Oakley and Paul Burgess, and it acts as a really nice sort of case study to sort of illuminate this process. And also highlight the fact that not every landslide-inducing storm in California comes from an atmospheric river. So this storm is called a cutoff low storm. So it's different from an atmospheric river. So this is like a low pressure system that gets cut off from the subtropical jet stream. So it's this big rotating thing that then gets isolated and just stays in one place and rains for a long time. And that configuration is kind of inherently unstable. And so what happens is you produce lots of convective thunderstorms also, or you can, let's say. Right. And so what happened that's what happened here with this cutoff low storm in April 2020. The system lingered in Southern California, and then as sort of the center of the storm migrated over in the Encinitas, San Diego area, it produced some thunderstorms that triggered a bunch of landslides and debris flows in the area. And we can kind of see that reflected in the nearby rain gauges again. Nina put this plot together. So you can see kind of the start of the cutoff low system where it starts raining, and you have a couple days of sort of low intensity precipitation. And then here's the point where the storm is sort of centering over the town. Excuse me, I'm sorry, I'm getting over a cold. My voice is a little scratchy. And you can see right on around April 11th, this big spike, especially in Encinitas, where this thunderstorm produced a short burst of high intensity rainfall, right? And that produced a number of debris flows across the area, including this one. Paul Burgess at one point, I think, gave a Landslide Hazards Program seminar about this event. This was a debris flow that inundated the San Diego Tennis Club in Encinitas, where the tennis court acted as a pretty nice little debris basin for the debris flow. And so Paul, being his intrepid self at the beginning of the COVID lockdown in April 2020, managed to sort of overcome the logistical hurdles and go out there and survey a lot of the landslides that happened in this neighborhood. And so you can see in this area, so you can see the landslides that Paul mapped are these blue dots, and then we have the GPS tracks that he traveled in black there. So we didn't get full coverage of this area, but in the short amount of time was able to document quite a few landslides around Encinitas. And so now we can sort of zoom in and we'll look at the sort of 20-year history of rainfall and AWI and how this A-star parameter looks for this event, right? Okay, so now we're zooming in. So to do this, the rainfall data set that we're using is the NOAA CNRFC, the California Nevada River Forecast Center, has a 6-hourly gridded precipitation data set for the entire sort of California, Nevada area that goes back to about 2003. So we use that data set because it works nicely with our entire sort of study region, the state, and has sufficient sort of resolution, spatial and temporal resolution. And so what we're showing here, this is the 6-hourly rainfall on the top. Whoops, I did it again, I pressed the wrong button. And on the bottom here, I'm showing now the AWI model for that rainfall data set. And you can see this is, I cut this off at 0. The negative AWI values are when you're still in that antecedent condition before that RO parameter. So here you're below the spout in our barrel. But most of the years you rise above it. And so what we can do to calculate the 10-year recurrence interval is we take the annual maxima for each water year, and we can plot a histogram of those. And then we can use extreme value statistics and fit an extreme value distribution to those data. In this case, I think it's a Gumbel distribution. And so once we have that equation, we can back out the recurrence interval for any amount of time. So here I'm showing the recurrence interval of 10 years here. And then when we plot that on our AWI plot, we can see that our April 2020 event through that 20-year climatology winds up being the most extreme event and rises over that 10-year recurrence threshold. So similar to the 10-year recurrence of our star, but now has a little more dynamic ability. Right, and so what does this look like in map view? So here I'm showing you now a map of the maximum 48-hour precipitation for this event. You can see that this is more like the typical California where you have hundreds of millimeters rather than 1,000, right? So a pretty different landscape. So here's the San Diego area pulse slides down here, but we can see pretty similar rainfall totals across the transverse range into the Southern Sierra and in San Diego. But when you normalize that to the 10-year AWI, we see this nice bullseye of above threshold A star right around the zone in Encinitas. So that's quite encouraging response. And we can zoom in and we can see a little more clearly, we get these contours of AWI or of A star that sort of surround this population of landslides. Right, and again, we don't know if there are more landslides mapped out here. There's a few examples that'll show later from National Weather Service storm reports that suggest there were, but nobody's mapped it definitively. Right, and so, sorry, apologies. So that was a good example from a late season storm, but we really wanted to test how important the antecedent aspect of this metric was. So the question really is this better than R star or not? And so an extreme early season storm should be the test of whether or not A star is a little bit more useful in the context of California. And so luckily we were gifted with a really extreme event that occurred in October at the beginning of the water year the following year in 2021. And so this is a movie from CW3E showing the track of these, it's actually a forecast, but of the atmospheric river plume that sort of inundates California in a few days in late October. And you can see this IVT is exceeding sort of 1,200 kilograms per meter per second, which wound up being the highest on record for the entire October climatology in Northern California. So this is like quite an extreme storm, and the rainfall totals were really high, but very few landslides were actually observed given the amount of rainfall totals that existed there. Unsurprisingly, because the soils were so dry, the response was that, well, yeah, the soils just were able to take that amount of rainfall before things really went awry. There were a few pretty decent isolated landslides, but nothing in that sort of strong regionally distributed landsliding that we observed from later season storms. And so we can kind of go through the same exercise. And here we're looking at the 48-hour rainfall totals. Excuse me. So here we can see that really high rainfall totals in Northern California here, Northern Bay Area, or the Northern California Coast Range and Sierra Nevada. And then when we look at the 48-hour rainfall anomaly, this R-star metric, we can see we get this sort of big blast, this fire hose of anomalous rainfall from the Bay Area all the way up to Lake Tahoe. But then when we factor in the antecedent precipitation, when we look at the results and A-star results, we don't really see that same response, right? Here, because we have that antecedent term baked into the model, we only get there were a few isolated rock slides actually here in the I-80 corridor around Tahoe. There was some in there was one big rock slide in this is the Feather River area here, and some in the Northern Bay Area. So there were drips and drabs of things, but nothing like what you might expect from a map like this. So this suggests to us that we're kind of going down the right path with a metric like this. Okay. So now what we can do is we can apply this to a few other landslide inventories to see whether this A-star metric is consistent across different events where we have good mapped landslides. And so Sky Corbett did a really nice job. He's actually, we're using the other three events were all mapped by Sky here. And these two events in the middle were done for our analysis. That includes some pretty big storms that happened in California in the past 20 years, including this one, the second one. This is the January 10th, 2005 storm that impacted the Southern California town of La Conchita. So some of you may know that La Conchita landslide. It was very litigated. It was a tragically deep-seated landslide that buried a couple houses in the town of La Conchita, but it also produced hundreds, or if not more, thousands of debris flows in the drainage behind this. This storm actually had an impact all the way down through Southern California and Orange County. So it was a really big event, but we had nice imagery, pre and post-event imagery here, so Sky was able to map these slides. And then we had another pretty big atmospheric river storm on Valentine's Day of 2019. And here there was reports of flash floods and debris flows around, this is Eastern Riverside County. So this, for people who know, this is Mount San Jacinto. So San Andreas kind of comes around. And so this is on the way to Joshua Tree. And so we had a couple imagery data sets that we could use to map post-event landslides here. And then this inventory on the right represents landslides. It was over almost 9,000 landslides mapped in the East Bay Hills from that really wet winter of 2017. There were a couple back-to-back storms. And so unfortunately, we don't have independent timing for each of these events. So we're kind of lumping the like month of storms together for this. So take from that what you will, but the January 6th storm was the largest of those events. And so now what we can do is we can look at the triggering AWI for each of those storms and compare it to the 10-year recurrence interval for each of these storms, these inventories, which span kind of a range of background climatology. And so here I'm plotting this. And what this plot is showing us is actually inspired. This is a nice, it speaks to the power of the Landslide Hazards Program seminar that I was watching. Dave Cavagnaro, maybe it was 2 years ago, gave a really nice talk on post-fire debris flows and looking at anomalous 15-minute rainfall and how to plot just like this. And I realized, I was like, oh, what a great way to visualize something like this. And so what we're seeing here, so all these different colors represent landslides from these different events. I actually included a fifth inventory here from an event in the Chino Hills in Southern California shortly after the La Conchita storm. That's in purple. And so the triggering AWI for the landslides here is shown on the y-axis, and the 10-year recurrence interval AWI is shown on the x-axis. So what this bold line is here, this is the one-to-one line. It's scaled a little bit differently so I can include this population up here. But what you can see is that 97% of the storms in this in these sort of 12,000 landslides plot above this 10-year recurrence interval threshold. So that really suggests that we can use this 10-year recurrence as kind of a floor above which we expect conditions sort of consistent with distributed shallow landsliding, right? So that's a very encouraging result. Okay, and so now what we can do is look at the climatology of AWI for each of these other inventories, for at least the three other ones that Sky had mapped, and see if it's similar to what we saw in the San Diego example, right? And so here we're going to go down. So what I'm plotting here in each of these plots, so here's the San Diego record again, except now instead of showing AWI, I'm showing A star. So this A star equals 1 is equivalent to the 10-year AWI. That makes sense, right? And so what we see in the La Conchita event, so the blue stars are the landslide times. And so what we see similar to San Diego at the 2005 La Conchita event, we have a big spike above threshold. Similarly, our January event and even the February one pokes above this A-star threshold. And similarly in our Riverside County event. So for each of these 4 events that we mapped wound up being the sort of events of record for these 20-year climatologies of AWI in each of these areas. And you can see in the Riverside, there are a few other examples where things went above threshold. This was the same storm, the same as the La Conchita, the January 2005 storm. And this is an event where we don't have landslides mapped in 2011 here, but there were reports of distributed landslide in eastern Riverside County for what it's worth. So I don't think that's a false positive, but don't know for sure. Okay, so so we don't have records of landslides for all of these places going back all these years. But what we do know, at least in the case of the East Bay event here, is that this type of regional landsliding, where you're getting thousands of landslides, hadn't been seen in the East Bay Hills since 1998. That El Nino year produced a similar response, and those landslides were mapped by Jeff Coe and Jonathan Gott in the early 2000s. So this does give us confidence that we're sort of capturing, that this metric can capture these sort of large distributed landslide events. Okay, so now what we can do, now that we know that index, that sort of the point scale works, seems to work pretty well, we can try to now map A star in space and time, right? And then we can even derive a metric that sort of describes the total footprint of above threshold area. And so what I mean by that, so we have this term we call landslide potential area, or LPA. And really what it is you can think of it as the total area of hill slopes that exceed that threshold during a storm, right? So you can imagine a blob in here of A star being mapped, right? And so these red pixels are showing kind of all the hill slopes in our study area below the sort of 8,000-foot snow line, because a lot of these are wintertime storms. Above that, you're just getting snow, so we mask out those areas. Okay, So now what we can do is we can add in a couple more events beyond our 4 inventory events or our 5, and we can look at a couple more storms that may be lacking inventories, but we know have its reports of landsliding. And so, and what I'm showing here now is a grid of these 9 different storms in the catalog we've put together, sorted from our smallest event, our October 2021 event, almost essentially a null event, to our largest event here, which was the New Year's 2005-2006 storm. For people in the state who remember this, it was a really big event, tons of flooding in the state. There were landslides reported from Lake Tahoe area to Marin County, up through the Coast Range and all the way to the Oregon-California border along Interstate 80. And so what we can do now is Nina pulled information from each of these storms about their synoptic features, whether they're an atmospheric river, the strength of that atmospheric river, which we'll talk about in a few minutes, any mesoscale, finer scale features in those events. And so now we can use that to sort of compare these events of distributed landsliding from our threshold to these meteorological characteristics. And but one of the things that maybe you're noticing right now, and certainly the reviewers of this paper notice, is that when you're looking at these little teal squares here, represent sort of the extent of these landslide inventories, right, which are quite small relative to the entire footprint of these above threshold areas. So the question, the logical question to ask is, well, how valid are these areas outside of these boxes, right? You know the boxes well, but how well are you capturing landslide areas outside of that? And that's a hard thing to answer when we don't have map data for those areas. But luckily, we can lean on some really nice work by the California Geological Survey, looking at a series of storms from this past year in January 2023, where we had another extreme storm sequence hit the west coast of California, producing a number of landslides that were then tabulated. The reports of these landslides were tabulated by CGS and given, points on the map and timestamps. So we can now sort of compare. We can use that as an example to sort of compare the response from some of these atmospheric river storms to their spatial distribution. And so we're kind of doing a trade-off here between precision from these landslide inventories that we've mapped to accuracy in thinking about the broader spatial distribution. And so the 2 strongest events from this sort of sequence of 9 storms was one that came in on January 1st that really was like a fire hose right through the Golden Gate area, East Bay Hills, again, and into the Sierra Nevada. And then the second stronger storm on January 9th that really impacted the Central Coast, Southern California area of 2023. And so this was a situation, and we had USGS people in Sacramento dealing with emergency managers and people on the ground doing surveys. I was up in an airplane trying to survey landslides during these storms. And so it was a really big deal when it was happening. And so now what we can look at is the distribution of our above threshold A-star relative to these reported landslide databases, the reported landslides from this database. And so we can look and we can see at a course level, it does a pretty good job. We can see in the case of the New Year's storm, the January 1st, where we have these high concentrations of landslides is where we have the relative increases in A-star here, right? And though we're missing a big gap here, and again, we don't know if landslides just weren't reported there, or they were reported later, it's just hard to tell, or it's just a false positive, right? But it does sort of capture this zone down here. But one of the things you might notice is that what A-star is not very good at is capturing some of these isolated events that we see in Northern and Southern California. So the strength of this metric is really for these kind of bigger distributed landslide events. We had numerous debris flows in San Francisco and on the peninsula. I surveyed over hundreds of landslides in the East Bay Hills that aren't part of this data set, but yeah, and then so when we look at the second storm here, the January 10th event, we can see again a pretty good correlation between where these zones of high landslide density are reported and increases in this A-star parameter, right? And again, missing a lot of these isolated events, but capturing kind of the higher spatial density. And one of the things that allows us to do too is to see how that spatial density correlates to the underlying A-star. And so what this plot is showing is I binned each of these events into 15 arc minute bins and then looked at the landslide numbers in each of those. And so what you can see that as A star increases, you get higher densities of landslides, right? And what it does a bad job is when you have lower A star values, we get these isolated events that it's just not picking up very well. Okay. Great. So now that we have confidence in sort of the map distribution and the value of the LPA parameter, the landslide potential area parameter, we can start to compare that to the strength of the atmospheric rivers that cause these storms, right? And so the way we do that is we calculate what's called the AR scale for each of these events. And what this is a metric much like the rainfall intensity duration, except applied to IVT, that vertically integrated moisture flux in the atmosphere. So here you have on the x-axis the AR duration, and here the maximum IVT magnitude for that event. And so you can kind of empirically split these into exceptional, extreme, so a category of basically 1 to 5, where 5 is the most extreme and 1 is a low, right? And so they kind of applied these nominal, whether or not this rainfall is primarily beneficial or primarily hazardous, and we can kind of evaluate that directly, even though there's not much stock put into those categories, I should say. Okay, great. So now what we can do is we can kind of together look at the landslide potential area, which is on the x-axis, the intensity of A star, so like how intense, how above threshold were you in those pixels for each of those storm events, and also the associated atmospheric river scale for each of these storms, right? And that's what's shown as the colors to match the colors from the previous plot. And so one of the things that you might notice is there's not much of a relationship with anything here, right? So when we look at the relative intensity denoted by these A star, we don't really see an increase in A star for larger landslide potential areas, right? It's kind of, we have a few scattered events that are more anomalous in their anomalies. We also see that when we look at the largest events, they do correspond to large strong atmospheric rivers, AR4s and AR5s, but it's also some of the smallest events were AR5s and AR4s, right? So there's not much predictability from just looking at the AR scale alone, whether or not it's going to be a hazardous or just a beneficial event. And so that's quite interesting, but some more patterns kind of emerge when you look at the seasonality of landslide potential area. So here, now landslide potential area is on the y-axis, and on the x-axis is the time of year in which those storms occurred, right? And so what we see is this really interesting drop-off, and granted, it's only 9 events in this catalog, but from the largest LPA events are happening in December and January, and then as we get to February, they begin to decline in their footprints, and then decline more as the rainy season dies down, and the lowest being in October at the beginning of the water year. And so our hypothesis is this might correspond to actually the antecedent moisture conditions, which could be driven by things like the atmospheric river arrival frequency, like we talked about in the beginning, thinking about that coefficient of variation of rainfall, right? So, and what I'm showing here in this blue line is the average number of atmospheric arrivals along the U.S. West Coast throughout the water year. And we see a similar decline in atmospheric river arrival frequency. So that does seem to suggest that landslide potential area may scale strongly with storm frequency. And we can look at that a little more mechanistically. Instead of looking at just comparing it to AR arrivals, we can actually look at the antecedent conditions for each of these areas before the storm arrived. And so now what I'm showing on this plot is on the x-axis, I'm looking at the antecedent A star conditions before the storm. So for the pixels on the map in California that ultimately failed, that ultimately went, well, they didn't fail, but they ultimately went above threshold. If we look at what the A star was before the storm arrived, and then we plot that as a function of landslide potential area, we see a really strong relationship of what those antecedent conditions look like and the ultimate footprint of hazardous rainfall in the state, right? So this gives us kind of a mechanistic interpretation for why things like arrival frequency of atmospheric rivers matter for generating not only triggering for the scale of landslide triggering, right? And this jives with some recent work done by Lisa Luna and others, where they find a strong seasonality in the state of Washington using a different approach. Right, but even though this is a really strong relationship, it's not the whole story, right? When we think back to that case I described earlier from the Tuolumne River Canyon, for example, right? Those landslides were really only occurring where that NCFR parked itself over the Tuolumne River Canyon. So there's really a dance of these different sort of parameters at play, right? And we can have a few examples here to revisit kind of with this context of thinking about these different processes, right? So going back to our San Diego example, here's this landslides mapped by Paul Burgess. Here are some National Weather Service storm reports of debris flows from that event. And so these red contours are our A-star contours above 1. And here I'm showing the landslide potential area. So it's quite small, about 2,000 square kilometers for this whole area. And so the scale and what I'm showing here is the radar data that's showing this sort of convective thunderstorm that occurred right over where these landslides were, right? So these convective thunderstorms, this pattern probably has a lot to do with the scale of where you're seeing the above threshold A-star, right? And so when we go back to the Tuolumne example, again, we see these NCFRs. This is a time slice in the radar data, and we're showing the propagation direction of these things are going kind of to the southeast here. And so these are landslides along the Tuolumne River Canyon. These are the National Weather Service storm reports. And we can see this pattern of A-star as this sort of elongated thing that sort of directly mimics that sort of propagation of that NCFR across the landscape, right? So these things, so while antecedent rainfall matters, that pattern is being strongly dictated by the mesoscale processes in this case. But then we go to an event like the largest one in our catalog, right? This New Year's 2005-2006 event where we had flooding and landslides all over Northern California, right? And this is the largest LPA by, quite a bit more. It's about 40,000 square kilometers. And you can see the A-star contours are in red here. I didn't want to swamp the figure, so. But here, what we saw in the radar analysis of this was a persistent pattern of this structure, something akin to a mesoscale vortex, but the meteorologist Nina talked to didn't quite know what to call it. But this structure didn't have as high of rainfall intensities as these other events, but it did have this large spatial scale, and it persisted for a long time. But here, if you remember, this is a place where the antecedent conditions prior to the arrival of the storm were already really high. So by having this really high antecedent condition, it sort of allows the structure of the resultant footprint of hazard to reflect this feature, which may not be as strong as these others, but is sort of activated by the fact that now the landscape is so sensitive that it can be receptive to that sort of incoming storm feature. Okay, so with that, I'll go to conclusions. Like I just said, what this sort of analysis reveals is that, perhaps unsurprisingly, that the pattern and the scale of landslide hazard that you can portray using this analysis really reflects a dynamic interplay between these mesoscale and synoptic processes in California, right? And an encouraging result from this is that we can use an index like this A-star parameter, this climatologically normalized soil hydrology metric, that does seem to produce a reasonable threshold for distributed shallow landslide occurrence, at least in for the inventories that we looked at. So to me, this suggests that there could be pretty strong forecast potential in using something like this. It's simple, and again, we're not doing these deterministic slope scale investigations here. We're not modeling that. We're kind of looking at trying to generate large situational awareness at the sort of 10-kilometer scale, right? So for that metric, it seems to work quite well. And so lastly, while atmospheric rivers are clearly important for California, the atmospheric river scale doesn't actually provide that much information about predicting what the impact will be for that event. So it's really like the preceding storm frequency reflected in the antecedent A-star and the mesoscale features that really exert the control on a landslide potential area. And so with that, I can take questions. Thanks so much.